Welcome back to the next video, everybody. We are finally going to finish the proof of Ribet's theorem today. So let's get into it. Let's recall where we're at. Here's what we need to prove to finish the proof of Ribet's theorem. So this is theorem 5, Ribet's part. Let's let P be a prime that's at least 3. Let's let rho from GQ to GL2 of FP bar be irreducible and modular of some type N2 1 over QP bar. Suppose that L is a prime that isn't P, that divides N, whose square doesn't divide N, and that rho is unramified at L. Then there's a prime Q, which is -1 mod P that doesn't divide N, such that rho is modular of type Qn over L to 1 over QP bar. So we lower the level at the expense of raising it by Q, but Mazur takes care of the Q for us. Okay, let's also recall our 6 exact sequences from last video. So in the following, P is a prime at least 3. L is a prime not congruent to 1 mod P, which divides N, whose square doesn't divide N. M is N over L. J0n is the Jacobian of X0n. Phi0n FL is the quotient scheme here. So it's just the quotient of this mod at the connected component of its identity. Phi FQ is the group of connected components of JFQ, where JFQ is the mod Q reduction of the Jacobian attached to the Shimura curve from last time. And eta Q is TQ squared minus 1. Here are the 6 exact sequences. We'll call them Mazur 1, Mazur 2, and then Ribet 1 through 4. Mazur 1 is we have 0 to J0N0 FL to J0N FL to its quotient. Then we have 0 to this torus T0N mod L to J0N0 FL to J0M squared FL. Then remember, X parentheses something means take the character group of that thing. So then we have Ribet 1, which is 0 to the character group of JFQ to the character group of J0MLQ mod L to the character group of J0ML squared mod L. Then we have the same thing, but we switch the L's and the Q's. And then we have 2 more. We have 0 to KL to the character group J0ML squared mod L mod A to Q times that thing to phi star FQ to CQ to 0. Star means take the Pontryagin dual. Okay. And then KL and CQ were special Eisenstein schemes. Okay. And then we have the same thing for Ribet 4, but we switch the L's and the Q's. So this was all dealt with last video, and also the video before that. Okay, let's also recall the definition of multiplicities from last video. We know there's a maximal ideal M of T0 of MLQ, so the Hecke algebra at level MLQ, an embedding of K, which is T0 at level MLQ mod M into FP bar, a 2-dimensional K vector space V equipped with a Galois action, such that V tensored up to FP bar gives rho, the representation. So this is what it means to be modular of the level that we're assuming. And such that J0 at level MLQ of Q bar, and then take M torsion is isomorphic to V to the lambda for some lambda that's actually a natural number, so a strictly positive integer. So again, this all just means rho is modular of whatever level we were assuming it was modular of MLQ, right? Okay. Let's see. This lambda here is called the multiplicity at M of rho and J0 at level MLQ. Now, of course, rho has some multiplicity at M in the entirety of JQ of Q bar M torsion, right? We'll call that multiplicity mu. So in other words, JQ Q bar M torsion is isomorphic to V to the mu for some mu at least 0. All right, so this lambda and this mu, these are what are going to come together and allow us to argue. We're going to suppose rho is not modular of type MQ2 1 over QP bar by way of contradiction. And we'll show that using this and the 6 exact sequences above, that 2 mu is less than or equal to lambda, and 2 lambda is less than or equal to 2 mu, which is a contradiction because lambda is positive and mu is a non-negative integer. Okay, so this is all review. Let's get into the new stuff. Okay, I'm going to be skipping some details, particularly in this first part. If you localize Ribet 4 at the maximal ideal M, okay, so if you localize this guy at the maximal ideal M, localization preserves exactness. What do you find? Look, M isn't even in the support of this guy by construction. So you find that phi FL localized at M is 0. Okay, so this is one of the first things Ribet does. Okay, so what does that say? Well, that says that J0 FL, take the FL bar points and take the M torsion, that has to be isomorphic to V to the mu as K vector spaces. The reason for that is if you go to the definition of these multiplicities, you have JQ of Q bar M torsion is isomorphic to V to the mu. Okay, but then you just got done showing that when you localize at M, let's see, where is it? Phi FL localized at M is 0. Okay, what is phi? You just have to go back and trace through all these definitions here. Phi is the group of connected components, right? Okay, well, I just got done showing that when you localize at M, that's trivial, right? Okay, so this guy here basically then will descend mod L to the M torsion. That's all that's happening. That's just another way of saying that. Okay, so we have this. Basically, the definition of mu descends mod L to M torsion. Okay, SK vector spaces. Now, what that means is if you look at the K dimension of the character group of J mod L tensored up to K over the Hecke algebra T0 of MLQ, you just get 2 mu, right? This has dimension 2 mu because V is 2-dimensional. Okay, perfect. So this is one of the equalities that we'll need. Now, Ribet's second exact sequence here, okay, because I'm assuming that rho is not modular of level ML, these guys have to have the same dimension when we tensor up to K over T0 of MLQ as K vector spaces. All right, so pay attention also to the fact that the dimension K of this character group at level MLQ tensored up to K over this full Hecke algebra is the same as the K dimension of this character group tensored up to K over T0 MLQ. All right. Okay, go to Mazur's first exact sequence and replace N by MLQ. I'll let you go back up and read that exact sequence. Here's what you get. You get 0 to J0 MLQ connected component at the identity mod L to J0 MLQ mod L to phi 0 MLQ mod L to 0. Okay. You also know from Mazur's work that this guy is Eisenstein, which I defined last video. So that means away from the level, Hecke operators act as the prime index plus 1. Okay. So you can prove from that the M torsion of J0 MLQ of Q bar actually specializes when you go mod L down into J0 of MLQ connected component at the identity mod L of FL bar. In other words, this M torsion here kind of descends mod L, and you can kind of drop the torsion away. This all follows from Eisensteinness. You drop the torsion away at the expense of just moving to the connected component of the identity, essentially. Okay, so akin to Mazur's second exact sequence, which if you go back to the video, 2 videos ago where we built this exact sequence here, this was built as the result of a normalization map. Okay, akin to the way that was built, there's a normalization of the modular curve x0 at level MLQ mod L, and that induces a short exact sequence built almost the exact same way, 0 to this torus T0 of MLQ mod L, to J0 of MLQ 0 mod L to J0 of MQ squared mod L to 0. Okay, so this is basically like a cousin or a sister, I guess, to Mazur's second short exact sequence. Okay, I have assumed rho is not modular of type MQ 2(1) over QP bar. And you can check very quickly that basically in the same way that we showed that this guy had dimension 2 mu, similar logic shows that the K dimension of the character group of J0 of MLQ mod L tensored up to K is 2 mu. Okay. The next thing is Ribet shows that the Frobenius endomorphism of J0 mod Q is just Q times TQ. So in particular, a row of Frob Q has to act like a scalar matrix on the M torsion of J0 FQ's FQ bar points. Okay. Look, Q, I believe was, what was it? It was, if you go back up here, Q was assumed to be, where was it? Yeah, Q is -1 mod P. Okay, another way of saying that is that rho of Frobenius at Q is in the conjugacy class of the matrix 1, 0, 0, -1. Okay, now, Frobenius acts like a scalar on this M torsion piece, right? The scalar's got to be one of the pieces. So what does that tell you? You have a total of 2 mu dimensions to work with here, right? You're operating on a 2 mu dimensional space. You break into kind of you have 2 eigenvalues, 1 and -1, breaking you down into 2 pieces. So what must be true? The K dimension of the character group of JFQ tensored up to K has to be less than or equal to mu. Okay, basically your the k dimension is less than or equal to half of the 2 mu dimensions that you have to work with because you break into 2 pieces here. That's what's going on. Okay, you can apply this same reasoning to the maximal torus T0 of MLQ mod Q and J0 of MLQ mod Q. And you find similarly that the k dimension of the character group of J0 of MLQ mod Q tensored up to k is less than or equal to lambda. So these two guys are gotten by the same argument, essentially. All right. Crucially, I claim that the k dimension actually of the character group of J0 just at level ML squared mod Q tensored up to k is less than or equal to mu. So let's show this. First, note that eta Q, which I defined several slides ago, is actually in the maximal ideal M. If you use Ribet's third exact sequence, so this exact sequence here, okay, so the first kind of weird Eisenstein exact sequence, what do you find? Look, this is in M. So what's going to happen is, let's focus on these two guys. Okay, what's going to happen is, I mean, there's details to check here, but what happens is, because eta Q is in M, the k dimension of the guy, the character group of the guy that's on top of that quotient, so the character group of J0 of ML squared mod Q tensored up to k is going to be the same as the k dimension of phi star of FQ tensored up to k. Okay, this is all because eta Q is in M. And well, again, because eta Q is M, this is going to be the k dimension of the M torsion of phi sub FQ. Now, there's things to check here, but I'm just trying to give you an outline. Basically, we can't go through this whole thing. All right. So I'm still not done. I want to prove this. Right. So if you go to SGA 7, chapter 9, section 11, Grothendieck actually describes phi sub FQ as the character group of JFQ dual mod the character group of J prime FQ, where this kind of like upside down wedge here indicates just taking the Z dual, and where what is this J prime mod Q? It's actually just J mod Q with the dual T0 MLQ action, so the contra-gradient action. What I mean by that is if you take T and like T0 of MLQ, just have it act as T star, the dual of the endomorphism given by T. And the reason this actually makes sense is we're acting on Jacobians here. And one of the big things about Jacobians is that they're self-dual. So this actually makes sense in the first place. Okay, in particular, this sequence here is Hecke equivariant. Okay, then you have some work to do, which we'll skip. If you consider multiplication by P on this sequence, apply the snake lemma, and you take kernels for M, so you take M torsion, you end up with an injection of the M torsion of this guy into the character group of this guy tensored over Z up to FP and then take M torsion. Okay. So I wrote that here. Now pay attention to that. That's what's going to give us the result. Now Ribet shows using results from this right around the same section of SGA 7 and using a known description of the action of Frobenius at Q on homomorphisms from the character group of J mod Q to mu P, the P torsion, P roots of unity, that there's an exact sequence, another exact sequence, from 0 to the M torsion of Hom J mod Q to mu P to the M torsion of J of Q bar, where J is our Shimura Jacobian, to the character group of J prime mod Q tensored up to FP M torsion. Okay, look, by definition, we already know this guy. We already know this guy has dimension 2 mu, right? So these guys have, well, the conjugacy class of rho of Frob Q is in that conjugacy class of, what was it? It was like 1, 0, 0, -1, right? So these guys have to have the same dimension, right? Which has to be mu because this guy has dimension 2 mu. But look, if this guy has dimension mu, then this guy has dimension less than or equal to mu, right? If this guy has dimension less than or equal to mu, then by this string of equalities, this guy has dimension less than or equal to mu, but that's what I'm trying to prove. See? All right. Wow, very technical, right? Very technical even as a sketch. So the claim is proven. Now I claim we have all the estimates that we need. So here we go. 2 more slides. We can finish now. If you go, we haven't used Ribet's first exact sequence yet. If you go back up to Ribet's first exact sequence, which I won't do, I'll let you do that. You find it says there's no tricks. K dimension of character group of J0 at level MLQ mod L tensored up to K is at most K dimension of character group of J mod Q tensored up to K plus K dimension character group of J0 at level ML squared mod L tensored up to K. This just follows immediately from the exact sequence. All right. Now, I'm just going to throw a bunch of estimates at you that we derived in this video. We saw that this guy had dimension 2 lambda. That was one of our estimates. We also saw that each of these guys had dimension at most mu. Okay, so what does that tell you? That tells you 2 lambda is less than or equal to 2 mu. Fine, whatever. Okay, however, we also showed that the k dimension of character group of J0 at level MLQ mod Q tensored up to K is less than or equal to lambda. And the k dimension of the character group of J mod L tensored up to K is 2 mu. Throughout, I mean, just go back. This is all in the video. Okay. We also saw at the very beginning, though, that this dimension here equals this dimension here. Okay. Which is this dimension here. Okay. So these are actually the same. Well, that means 2 mu is less than or equal to lambda. Okay. But 2 mu can't be less than or equal to lambda if 2 lambda is less than or equal to 2 mu, if mu is a non-negative integer and lambda is a positive integer. So there's your contradiction. There's Ribet's theorem. Okay, theorem 4, Mazur's part, and theorem 5, Ribet's part, easily imply theorem 3, which is the major result of the chapter, which is the result sort of that we used in chapter 1, modulo discussions about the level. In particular, we get Ribet's theorem from chapter 1 in the case n is square free and p is a prime that's at least 3, which is the only case of Ribet theorem that we'll need for the proof of FLT, as we saw in chapter 1. Now, I am going to, basically because of this n square free assumption, which I don't actually believe I included in my discussion of the proof of Fermat's last theorem in chapter 1, I'm going to make a video, at least one video starting probably tomorrow, about the levels of the forms that come from Langland's tunnel. Okay, because that's kind of one loophole we need to fill in if we're only going to believe Ribet's theorem in the square free case, basically. All right, so I will see you all tomorrow, I think. Thanks for watching, and I'll see you then.